Welcome back to another lecture on space robotics. This time, we will explore the evolution of technology that enabled our space robots. By the end of this lecture, I hope you will be able to examine how key technologies have advanced our space robot capabilities to enable more complex and autonomous missions. Remember this slide? In this lecture, I'll talk about the enabling technologies that enabled these more basic capabilities earlier in history to the more advanced capabilities in modern times. As a reminder, the yellow verbs are those proven capabilities and the orange verbs are the unproven capabilities. And we also see levels of autonomy from proven to unproven. Let's start with the very beginning of any space mission deployment, launch. The very first rocket to reach space was the V2 rocket in 1942. The V2 rocket is technically a German ballistic missile of World War II, but is also the forerunner of modern space rockets and long-range missiles. The critical technology that enabled V2's unprecedented flight beyond the Kármán line is the development of the liquid fuel rocket engine, which allowed for greater thrust control and efficiency. During this time, the Germans were able to mass produce highly complex, precision machine parts and materials that were advanced enough to survive supersonic flight through the stresses of atmospheric exit and re-entry. The next notable technology evolution in rockets is embodied in R7. USSR's rocket successfully placed Sputnik into orbit and, pun intended, launched the space race. The difference between the V2 rocket and the R7 rocket is the first practical use of a parallel staging where boosters jettisoned mid-flight to reduce weight. To insert our satellite into orbit, the rocket can't fly willy-nilly anywhere, so advanced guidance systems of sensors and computing enabled R7 to get to the right magnitude and direction of velocity to place Sputnik in its orbit. Other advances in propellant and manufacturing enabled higher thrust and larger structures. Since then, we have sent spacecraft out of our solar system into orbits around Mars, and we're working toward taking off from the surface of other bodies using reusable rockets like Starship. To enable Starship, major technological advances come from the propulsion system, the manufacturing of large structures, and more advanced navigation that increased onboard autonomy. Starship's first successful demonstration was in 2023. The next step in an orbiting space robot's advancements is simply the capability to power on and communicate. The first space robot to do that was Sputnik in 1957. Its power supply are these 3 silver-zinc batteries, outputting 1 watt of power with a mass of 51 kilograms in the shape of this octagonal nut, and then this radio transmitter was slotted into that hole. Sputnik operated for 22 days. In 1977, we sent the Voyager satellites, a set of twin probes, into our outer solar system to visit our gas giants. But upon completing their initial mission in 1979 to 1989, they continued to venture beyond our solar system, leaving our solar system in 2012 and 2018. They are the longest operating missions and the only spacecraft to explore interstellar space, still sending us scientific information to our deep space network. They are able to survive and talk for this long due to their power source and high gain antenna. The Voyagers were equipped with 3 radioisotope thermoelectrode generators, each which generated 470 watts each at the time of launch, and here they are. That's nearly 500 times more power than our first satellite, Sputnik, in the span of 20 years of development. The radio and antenna, which are seen here, are much more powerful than Sputnik's as well. Our ground stations are also more capable to receive weak signals. The enabling technologies for basic space robot functions reside in advances in power generation and communication systems. In 2018, we sent 2 shoebox-sized cube satellites to Mars, our first interplanetary cube satellites. The technology advances here emphasize miniaturization, the ability to achieve a lot in a smaller package. Marco, seen here, is 1/6 the mass of Sputnik, but survived more than 9 times longer as Sputnik, communicating hundreds of thousands farther away. The technology that enables Marco are its solar panels, the energy-dense lithium-ion batteries, which are somewhere in this spacecraft bus, and a clever transponder radio with a high-gain reflect array antenna, which is seen here. Next in our chronology of capabilities, let's explore the ability for space robots to observe. Sputnik was only able to beep and boop in 1957, but Explorer 1, seen here, was able to actually observe science in space in the form of a modified Geiger counter to detect cosmic rays, 2 micrometeorite detectors, and 5 temperature sensors. To describe the technology evolution of scientific packages that collect data in space is an overwhelming task that deserves a whole course in itself called Space Science Instrumentation. But this is not that course. We're going to move on and focus on robotic technologies. Next in our evolution of capabilities is navigation, which has many different types of sub-capabilities that I'll cover in a bit. To achieve navigation, the first technology that needs to be established is a way to thrust. The first thrusters to successfully be demonstrated in space were on board the US Navy's Transit 1B, seen here. The thruster outlets are seen here at the end of these spindly arms. These thrusters enable a satellite like Transit 1B to change its velocity, which affects its orbit, and to control its attitude or orientation. Transit 1B also laid the foundation for navigation sensing and algorithms, such as Doppler shift tracking, gyroscope and magnetometer incorporation, and onboard computer clocks. A more advanced navigation capability is to be able to fly by other celestial bodies for the sake of observation and gravity assist. In 1962, Mariner 2 became the first successful planetary mission by flying by Venus and discovering that radio brightness was consistent with the hot surface. The enabling technologies were a more precise Doppler tracking system extending from low Earth orbit to interplanetary travel, a more powerful cold gas thruster system that provided more velocity change, a more comprehensive attitude sensing control system, and the first hints of logic-based sequencing on board its computer. In 1973, Mariner 10 became the first spacecraft to use a gravity assist to reach another planet. That gravity assist was around Venus to reach Mercury. To achieve this gravity assist, the navigation system had to be very precise and well-timed, requiring more sensing, algorithms, and a more precise onboard computer clock. Now that we can propel ourselves farther into the solar system, the next capability in navigation is to then insert yourself into another body's orbit. The first successful orbiter of another celestial body was Luna 10. That happened in 1966. Luna 10 saw advances in propulsion and navigation. Instead of cold gas thrusters on earlier spacecraft, Luna 10 had solid propellant retro rockets. Its attitude control system was more advanced and implemented a pre-programmed timing-based sequence logic for lunar orbit insertion. The logic was done without an onboard computer, but this physical circuitry are the seeds of modern-day autonomy. The first successful orbiter of Mars was Mariner 9 in 1971. The technologies that enabled a Mars orbit insertion were again retro rockets. And let's bring back the mention of power systems to power a thermal system that warmed the orbiter during its long transit to Mars. And the last technology was the first onboard computer as we know them now. The last capability I want to talk about for orbital space robots is the capability to manipulate objects in space. The first successful demonstration of a robotic arm in space was Canadarm, seen here, on board the Space Shuttle Columbia during the STS-2 mission, launched on November 12th of 1981. While this mission didn't use the arm for manipulating objects just yet, the arm was teleoperated by astronauts on board the shuttle to demonstrate basic arm movement in space, joint articulation, range of reach, and stowage. It had 6 degrees of freedom and functions very similar to our arms. There are 3 different joints at the shoulder, elbow, and wrist, and 2 degrees of freedom for each joint, which I'm demonstrating here. Let's move on to planetary robot capabilities. The prerequisite to even demonstrate landing on a celestial body outside of Earth requires the capabilities of all of the orbital space robots that we were just talking about. The first robotic landing on the moon was achieved by Luna 2 in 1959. Luna 2 was a hard impactor, not a soft lander, meaning it crashed onto the lunar surface, but successfully confirmed impact and provided scientific data. To achieve landing on another body, there were 3 propulsive stages to the mission: the R7 booster and core rocket to escape Earth, the Block E upper stage to provide a final burn toward the moon, and then the final Luna 2 spacecraft to coast toward the moon and impact the surface. These precise and well-timed separations rely on navigational technologies we discussed earlier. Luna 2's instruments luckily survived impact and collected data, which speaks to the technological advances in materials to design and build an object that protect instruments after an impact of 3.3 kilometers per second, or 7,400 miles per hour. At this time in history, aluminum alloys had a history of being used in high strength to weight applications like in aircraft and missiles. Their use in spacecraft was an advancement for space robot design. After successfully achieving a hard landing, the obvious next step would be to attempt soft landings on other planets. The first soft landing by a space robot was on the moon by Luna 9 in 1966. Luna 9 was able to achieve a soft landing through a retro rocket, which we have seen used historically in orbital space robots to insert themselves into other bodies' orbits. But instead of being triggered by orbital cues, Luna 9's retro rockets were triggered by a radar altimeter tracking the altitude of the robot from the lunar surface. This will be a prerequisite for other, more advanced landing systems. After Luna 9 used its retro rockets to slow its speed to 22 kilometers per hour, it was ejected from its outer descent shell right before impact to reduce impact velocity of the precious payload inside. The inner payload was encased in a shock-absorbing shell that bounced slightly and unfurled its petals to guarantee an upright orientation, which you see here. This technology was critical for orientation-specific instruments and to communicate back to Earth. We see similar technologies advanced in the Mars Pathfinder lander launched in 1996. Here is a picture of the Mars Pathfinder lander. It's not this on top, but the lander is beneath that platform. After it had deployed its novel airbags, bounced across the Martian surface until a full stop, unfurled its petals to reveal its precious payload, the Sojourner rover, resting in the middle right here. Speaking of rovers, the next capability we need to talk about is the ability for space robots to move on planetary surfaces. The prerequisite capabilities and technologies that got us here were launch, observation, navigation, and landing, to be able to think about moving. Lunokhod 1, which is seen here, was the first remotely controlled robotic rover to move on the moon, traveling 10.5 kilometers over 10 months. It was different from any other space robot before its time, in that it had wheels and electric motors to move forward and turn. It built on a suite of developed power systems such as solar panels and batteries, as well as radioisotope heaters to help it stay warm throughout a cold lunar night. Lunokhod had 2 forward-facing TV cameras, gyroscopes, and tilt sensors for navigation. Its communication system allowed human operators on Earth to teleoperate the rover by peering through the camera feed and steering the rover through its motors, controlled by basic control logic. To offer another data point along the evolution of movement, Sojourner was the first Mars rover, part of the Mars Pathfinder mission we just described in the last slide. Sojourner, which is shown over here, moved 100 meters during its mission and had an advanced for its time onboard CPU computer and navigation software to automatically detect hazards and react. The level of autonomy spanned teleoperation, automatic operation of preloaded go-to paths, and semi-autonomous operations to prevent potential collisions. Nowadays, the most advanced planetary mobility robot is the Perseverance rover. It launched in 2021 and is still operating today. It has set records for Martian off-roading, including the longest single-day drive of 348 meters and the longest drive without human review at 700 meters, all thanks to its nearly fully autonomous navigation system, AutoNav. With our state-of-the-art navigation cameras and algorithms, Perseverance is able to generate 3D terrain maps, conduct real-time path planning, continuously drive, and avoid hazards to drive as far as we've ever driven on the surface of Mars. This image on the bottom here shows the trajectory of Perseverance from landing all the way from here, following this white tail, deploying Ingenuity all the way to where it is now. The next capability I'd like to talk about can be developed in parallel to mobility. Let's talk about sampling. Luna 16 is the first robotic surface sampling on another body, specifically the Moon in 1970. Not only did Luna 16 sample on the lunar surface, it also collected 101 grams of lunar soil and returned it to Earth. Another successful, unprecedented mission. Luna 16 had a motorized robotic drill to access subsurface samples as deep as 35 centimeters beneath the surface. These samples were then contained within the lander in a return capsule. As a bonus technology demonstration, Luna 16 lifted off from the lunar surface with solid fuel rocket ascent, which was the first successful demonstration of an ascent stage in space ever. I alluded to this in my first lecture, but a really exciting development recently was the successful Firefly lander, Blue Ghost. On board was the Honeybee Robotics Lister drill technology demonstration. This drill, launched in 2025, is a pneumatic drill, and it can drill 2 to 3 meters compared to the historical 35 centimeters, and even had embedded science instruments within the drill. Another way to sample on extraplanetary surfaces is to scoop soil with robotic arms and specialized end effectors, like the Viking landers did in 1976. Here's its little robotic arm and its end effector. This technology relies on manipulator technology previously developed on Earth and then space qualified up in orbit. Yet another way to sample a celestial body was demonstrated in 2005 by the Hayabusa mission, where an orbiting space robot was momentarily a planetary surface robot when Hayabusa touched down on the asteroid Itokawa to collect micrograms of dust and returned it to Earth in 2010. To interact with the asteroid, this space robot had to implement advanced visual sensing and navigation of the terrain to find an appropriate landing site to sample. The level of real-time processing necessitates higher resolution cameras, faster clocks, and more powerful computers. The sampling technology that enabled this mission is a touch-and-go mechanism specific to the dynamic nature of the spacecraft relative to the celestial body. That cone-shaped horn, which you can see over here, extended toward the asteroid, and when contact was made, the asteroid samples passively drifted into the horn and were captured. As we look into the future, the NASA Artemis program has laid out ambitious goals to live and work on another world. While previous robot capabilities of moving and sampling are necessary for prospecting for resources that will be useful for human persistence, we as humanity need to be able to develop the surface to build structures for our astronauts and robots, such as landing pads for rockets and habitats for humans. Regardless of what structure, we need to be able to prepare sites, modify terrain, utilize resources in situ, construct and assemble structures, deploy power systems, and transport material. We haven't yet flown any robotic missions that have demonstrated these capabilities, but here are a couple that are in development with beautiful artist renderings. Here is an image from the 3D printing architecture company Icon of a lunar robot creating horizontal building blocks for roads or landing pads through a technology called laser VMX. The laser that you may see at the end of that arm is sintering or melting lunar regolith into a solid glass-like structure, layer by layer, effectively 3D printing a solid object or structure from lunar regolith. The enabling technologies here are rover mobility, its robotic arm, and a high-powered laser, which have loose historical ties to the Curiosity and Perseverance Mars rovers, where lasers vaporize rock and soil targets for inspection, rather than for the purpose of construction. And here is an artist concept of NASA's RASER, or Regolith Advanced Surface Systems Operations Robot, which is an in situ resource utilization, or ISRU concept. Razor's primary function is to excavate and transport lunar regolith to processing facilities, where resources like water and oxygen can be extracted. The enabling technologies like Razor are its mobility, its miniaturization, but uniquely, its counter-rotating bucket drums that you can see here lifted up and then here digging into the subsurface. This design allows Razor to dig without relying on its weight for traction. That's how it's able to excavate so much regolith mass given Razor's relative low mass. This opens up possibilities to scale production of regolith with many Razors, but not that many costly launches to get Razors to the surface. There are other exciting concepts out there that we don't have time for in this lecture, but you may have the opportunity to explore these yourself in this week's assignment. On to aerial space robots. The first robot to leverage a planetary atmosphere is Venera 4, and it broke technological records in numerous ways. Venera 4 was the first spacecraft with an ablative heat shield to successfully use a thermal protection system in a planetary atmosphere other than Earth's. Venera 4 was also the first spacecraft to use a parachute to slow a probe after atmospheric entry. Entry, descent, and landing happens very quickly, which is an excellent use case for autonomy. In Venera 4's case, the automatic descent sequencing used sensors and timers to trigger the heat shield jettison, a two-stage parachute deployment, and instrument activation. Similar but more advanced technology successfully landed the Huygens probe on the surface of Titan in 2005. Here's an artist's depiction of the Huygens probe concept of operations showing the heat shield in the corner, and then the 3 stages of parachute deployment before ultimately landing on the surface. After descent, a capability of drifting is opened up. The first aerial robot to drift through a planetary surface is Vega 1 in 1985. To achieve this, a heat shield separation system automatically disconnected a lander from this balloon drifter, which requires the lander to have an altimeter and logic on board to handle such a sensitive deployment. Vega 1 inflated a constant pressure helium balloon into Venus's atmosphere shortly after atmospheric entry and drifted at 54 kilometers of altitude for 46 hours, collecting data on winds, temperature, pressure, lightning, light levels, and cloud structure in the planet's most active cloud layer, both day and night. The technology that enabled the driftings was the first demonstration of a balloon on another planet and the proper materials to ensure survivability, such as the usage of an inert gas within the balloon to avoid combustion, coating the balloon with Teflon, which is resistant to high temperatures and chemical corrosion, and the shielding of an electronics box with a white corrosion-resistant coating to reflect heat and resist sulfuric acid corrosion. The evolution from the previous aerial slides started at resisting an atmosphere to going with the flow of an atmosphere to where we are now, actively controlling an aerial vehicle with an atmosphere. Active flight was demonstrated for the first time by the Ingenuity helicopter in 2021 as an add-on technology demonstration of the Perseverance rover pictured there in the background. The technologies that enabled Ingenuity to achieve flight are its ultralight and also high-lift rotor system, its autonomous flight software, its compact batteries and solar panels, and its miniaturized avionics and sensors. The atmosphere on Mars is 1% as dense as Earth's, while Mars's gravity is 40% as much as Earth's. As Ingenuity's mechanism for creating lift diminished faster than gravity, Ingenuity had to be very small and efficient to achieve flight. Ingenuity's mass ended up being 1.8 kilograms, which was only possible due to the miniaturization and efficiency gains achieved through the decades of research in batteries, sensors, and computers. In fact, the computer onboard Ingenuity was a Qualcomm Snapdragon 801, which is the same chip used on the iPhone 5S and the Samsung Galaxy S5. Just like how we joke that calculators are more computationally advanced than the Apollo-era computers, we can also say that your phone that you have in your pocket has a more advanced computer than the helicopters on Mars. Despite this, a certain level of autonomy was necessary to even consider this mission. The dynamics of flight move very quickly, so there is no option of using teleoperation for a 10-second flight when the communication delay is likely going to be 7 minutes long. While Ingenuity was not a fully autonomous mission in that the helicopter didn't pick science targets or plan its own flights, Ingenuity executed pre-planned flights autonomously through takeoff, stabilization, trajectory planning, trajectory tracking, hazard avoidance, and landing. These flight demonstrations are depicted in this lovely concept of operations where Ingenuity's flight data could be sent to Perseverance to scout terrain up ahead. From here on out, we are only going to speculate on technologies that will enable future space robot capabilities. While the ability to actively control flight has been proven, Ingenuity only spent 128 minutes in flight, traveled 11 miles, and survived 2 years. That's a fantastic technology demonstration, but for future aerial vehicles in space, we need to be able to cover more ground and do more science, which also means carry more mass during flight. NASA's Dragonfly mission, which is seen here, is scheduled to launch in 2028, and it will explore Saturn's moon Titan using a rotorcraft lander that can fly between and sample diverse sites, covering more than a projected 175 kilometers, or 108 miles, over its 2.7-year mission. To achieve meaningful coverage of a planetary surface, Dragonfly will leverage Titan's very dense atmosphere, low gravity, and 8 rotors to generate a massive amount of lift and precision flight to carry 450 kilograms of mass. Due to the 2.5-hour communication delay, the level of autonomy that is targeted for Dragonfly will be higher than Ingenuity in that flight trajectory planning, safe landing spot selection, and science operations will all have autonomy. This autonomy is enabled by more advanced sensors on board the octocopter, like LiDAR, IMU, and stereo cameras. With more sensing and computation and the cold cryogenic environment on Titan's surface, a radioisotope MMRTG and battery power will provide a sufficient amount of power to the multi-core CPU to run autonomy algorithms and have Dragonfly survive the night. Since we've never conducted a space robot mission in an underwater or subsurface ice environment, all of these technologies range from conceptual to terrestrial experiments. To even get to the ocean underneath Europa's icy shell, we need technology to drill or burrow through at least 3 kilometers of ice, where the surface of the ice is 100 degrees Kelvin or negative 173 degrees C. The technologies that would enable robots to burrow beneath the ice include a thermal-mechanical penetration system, a persistent compact power source for cryogenic applications, and communications through ice. These technologies are highlighted in the NASA Cryobot mission concept, pictured in that corner. NASA's Cryobot, an eel-like robot, is set to search for life on Jupiter's Europa and Saturn's Enceladus moons. A lander will deploy a self-contained cylindrical probe that utilizes nuclear power to heat and melt the icy crust beneath it. That probe leaves a series of radio beacons in its wake to relay data between the probe and the lander at the surface. The power source will most likely have to be a radioisotope power system, which doesn't have as much of a technological obstacle, but more of a sourcing issue with the Department of Energy. The technological challenges reside in the drilling and the communications. Briefly, NASA has explored fiber optic cables to provide a tether between the probe and the surface lander, but there are concerns about the cable's survivability and performance when the ice layers shift along the length of the cable. NASA has also investigated alternative wireless methods like radio frequency, acoustic, and magnetic transceivers. For drills and heat probes, we do have more technology demonstrations to discuss. In 2019, the Mars InSight lander began its attempts to burrow a probe into the soil to hopefully dig 5 meters. Unfortunately, the probe only made it a few inches before popping out. Another demonstration of drilling and burrowing technology is from Honeybee Robotics' Search for life using submersible heated ice drilling probe, or SLUSH for short. SLUSH is a thermomechanical drilling system that was tested at the Devon ice cap in the Canadian Arctic, achieving penetration depths of up to 1.8 meters. Here are some lovely pictures of the SLUSH drill in testing in a lab environment, what that borehole looks like, a beautiful glamour shot of the probe encased in ice after it had done its drilling, and then in-field testing. Once a robot makes it through the icy shell, the next capability we need to access are these aquatic or icebound environments. We need the robot to be able to slither in ice, through ice, or swim through water. NASA is developing SWIM, or Sensing with Independent Microswimmers, to deploy a swarm of tiny autonomous robots to explore the subsurface oceans of icy moons like Jupiter's Europa and Saturn's Enceladus. Deployed from the previously discussed cryobot, these microswimmers aim to enhance the search for extraterrestrial life by accessing environments beneath thick ice crusts that are otherwise challenging to explore. The technology unique to this capability is the underwater propulsion system. On SWIM, it's propellers and steering flaps, which enable controlled movement through liquid environments. As of 2024, NASA JPL tested these prototypes of this SWIMbot and successfully demonstrated navigation and control in a swimming pool, seen here. Once a space robot can reach an ocean environment, it needs to be able to navigate. What you're looking at here on this slide is a glimpse into the future of extraterrestrial ocean exploration. This submersible, developed in partnership with WHOI, the Woods Hole Oceanographic Institute, and NASA's Jet Propulsion Lab, is testing something we've already seen work spectacularly in space: terrain relative navigation. The same technology that helped Perseverance land autonomously on Mars and powers the Ingenuity's helicopter's flights across the Martian surface is now being adapted for use underwater, in one of Earth's most extreme environments. On this expedition, aboard NOAA's Okeanos Explorer, the Orpheus submersible is testing a cutting-edge system called XVIO, short for Visual Inertial Odometry. It works by matching visual patterns like rocks, shells, and corals on the ocean floor, much like a traveler recognizing landmarks on a road trip. Combined with precise motion sensors, XVIO builds a 3D map that helps the vehicle navigate, remember where it's been, and decide where to go next, all without GPS. And this is more than just staying oriented. The goal is to use this system to identify biologically rich and geologically interesting regions, and eventually allow multiple robotic explorers to work together autonomously in extreme and remote environments like Europa's or Enceladus's hidden oceans. It's another step toward making deep space underwater navigation a reality, starting right here on Earth's seafloor. Let's finish with the capability of sampling underwater or in icy environments. Meet BRUI, the buoyant rover for under-ice exploration. Designed at NASA's Jet Propulsion Lab, BRUI was tested between 2012 to 2019 in some of the harshest environments on Earth, beneath an Arctic lake in Alaska and beneath the Antarctic sea ice. As a rehearsal for something even more extreme, the oceans beneath the ice shells of Europa or Enceladus. It doesn't swim, it rolls upside down, so the ice is on top and then BRUI is turning its wheels underneath the ice shell. It rolls, using buoyancy to cling to the underside of the ice and move steadily along the ceiling of its world. This unique design gives BRUI the ability to stay close to the ice-water interface, a zone that could be rich in nutrients and microbial life, both on Earth and beyond. As it rolls, BRUI samples the environment with a suite of onboard sensors, measuring dissolved oxygen, salinity, pressure, and temperature, all key ingredients when looking for signs of habitability. The Antarctic deployment is more than a tech demo. It's a test of endurance, sampling, strategy, and navigation in conditions that closely mimic the alien ocean worlds we hope to one day explore. Welcome back to this slide on the summary of capabilities, but what we'll see here is now that I've attached dates, for when the capabilities were first demonstrated successfully in space. With the extra dimension of time listed here, we can see trends of dates increasing as we go down in each type of space environment, as each capability higher on the list is a prerequisite for capabilities lower down on the list. And like we observed before, dates go up the farther right in space environments we go due to the accessibility issue. Maybe one of you will contribute to the first successful demonstration of development or aerial coverage, or participate in a mission sending a robot to an icy moon or ocean world. While talking about these various technologies, I've been weaving in mentions of various levels of autonomy. Just as the hardware matured and enabled more capability, the software has followed a similar trajectory. This image shows the level of implementation and adoption of autonomy throughout the years, starting in 1959, where the primary modes of operation were teleoperation and automatic operation by the space race between USSR and USA. We saw several examples of teleoperation and automatic operation on the Moon and Mars and Venus missions. While we will never let go of teleoperation, as can be seen with the operation of robotic arms on the International Space Station, we are able to graduate the level of autonomy into semi-autonomous operations with the Mars Sojourner mission, which started in 1997, and has steadily increased capabilities today to AutoNav on board the Perseverance rover. Into the future, we are working towards full autonomy for the sake of deep space exploration robots and robot assistants that can conduct onboard servicing, surface exploration, and help humans live in space like in the Artemis missions. Wow, we have covered a lot of material, but I hope that you could follow some trends of key technologies that have advanced in space robotics and how these robotic technologies enabled greater autonomy and mission complexity. See you next time.